Okay, here's my inference video. This is going over chapters 7 through 12. One quick thing I want to remind you guys of is that we only went through chapter 11 for our class material. Chapter 12 is still testable. It is still a possibility that it'll be on the actual AP exam. It just historically has been very, very, very small proportion of the test, so I took the calculated risk of just not going over it at all this year. If you're at all worried or if you have some time, you might want to take a look at that, just have a basic understanding of it. But if you want resources, I have plenty. If you want to go over anything with me, just let me know. All right, we're going to go over these 5 questions from our quote-unquote test from Tuesday. Apologize for this being erased a little bit, but we're going to go over chapters 7 through 12, so just the basics of sampling distributions. What is a sampling distribution? Confidence interval, significance tests. And then we had all these different words that involved error. So type 1 and type 2 errors are actual errors being made based on significance tests. And we just talked about like the hypothetical options of what those could be. Standard error and margin of error go more with confidence intervals, and they are not errors in calculations. It's just talking about the idea of a sample being slightly off from the actual number in a population. So these are the things we're having the most trouble with when it comes to computations, just because we were forgetting the formula. So that's going to be probably what a lot of today's focus is going to be on, because y'all can do the confidence intervals in the test and the calculator for the most part. We're pretty good at this. We're still having trouble when forced to use formulas, how to use them. So we're going to focus on that. All right, number 3 was the first one in this section. I actually already worked through this one, so I'm just going to show it to you guys. But one thing I like to do when I'm reading through a problem is skip to the bottom. So it says, we're talking about degrees of freedom in a chi-square test, and then I would go through and read it for real. So it says we're doing both men and women. So I set it up where I had males versus females. And then it gave us 3 different answers they could give us in a survey: in favor of, not in favor of, and no opinion. So there's 3 different responses. Degrees of freedom for a two-way table like this, it doesn't really matter if it's homogeneity or independence test. It was the number of rows minus 1, so there's 2 rows, so 2 minus 1, 1 row left. And then number of columns minus 1, so 3 rows minus 1 is 2. Multiply those together, degrees of freedom is 2. This was just a diagram I did, so if you have 2 rows and you take one of them away, and you have 3 columns, you take one of them away, the degrees of freedom is how many cells do you still have left. So in case you like that visual. So that's number 3. All right, number 5, I already started marking up as well, so jump in on this one. Again, if you flip to the or you skip to the bottom, it says we're looking for a smallest sample size that will result in a margin of error of 0.1 or less for a confidence interval. So honestly, I could put less than or equal to, really. All right, so then if I read back through the rest of the problem, they gave us a standard deviation of 1.5 based on previous research data and an estimation. And then they also gave us that we're doing a random sample. They don't give us the sample size, because that's what we're looking for. We're looking for the sample size. And then it tells us we're doing a 99% confidence interval. So if you remember your formula for margin of error, we're going to have to find what's called a critical value, and that 99% is how we find that critical value. So the basics of margin of error is you have a critical value, and this is on the formula chart, times the standard deviation of the statistic. Okay, it just depends on if you're doing means versus proportions. So if it's proportions, it looks like this. If it's for means, it looks like that. So the formula the formula chart just says critical value times standard deviation of the statistic, but then it does go into more detail about what the standard deviation looks like for means or proportions. Okay, so from what we've been given, since we're given a standard deviation, it looks more like we're doing this. And think about what they're talking about. They're looking at the age at which children begin to walk. You can't really do a proportion of that, but you can take the average age. So this one makes more sense. We're doing means. We definitely already have the standard deviation part, so I'm going to go ahead and fill that in over here. We've got 1.5. I don't know the sample size. That's the whole point. I know the margin of error, the result needs to be no more than 0.1. So the trick here is we got to figure out how to find that critical value. Okay, so if we're trying to find how far, remember a critical value is saying, okay, well, we have an interval, We know that 99% is what we want to have in our interval, so how much data is left in the wings? Well, that's 1% left. Cut that in half, so you have 5%, or sorry, can't do math in my head anymore. 100 minus 99 divided by 2 divided by, so we have 0.005 of the data. That's a proportion in each of these wings. So the critical value is finding like what location am I actually at. So if you know the area but you don't know the location, that's an invert. So I'm going to go to my distribution. Get a little closer. We're doing means. I'm going to go to invert t. Area 0.005. Here's the issue. We do not know the degrees of freedom because the whole point is that we don't know the sample size. So here was the one scenario where even though we're doing means, we have to do invert norm because we don't, you have to go back to quit and invert norm. We don't know the mean, so we have to just go with the best thing we can do, which was finding a z critical value for a t, even though it's not ideal. So put your area in for 99% confidence. And that gives me, remember the positive negative didn't really matter because I just found this side, but it's the same thing on that side. So it was 2.58. So that is my critical value, 2.58. All right, from here you can do algebra and try to solve for that n. But the other option is, since you're given choices, you could just sit there and see which one would end up working. It did say which of the following, which is the smallest sample size. So if it's me, I'm going to start over here. So 2.58. You can even make a fraction here if you want to. Actually, I would do 2.58 times. You can always make a fraction if you want to. 1.5. Oops, I'm pushing the wrong buttons. I apologize. Square root of, and then so we go ahead and try a 400, and so if it ends up being less than 0.1, this would be the answer. Nope, too big. Okay, now here's a nice thing. If you haven't figured this out, you can copy and paste, and so you don't have to type all that again. Just use your up arrow until you highlight and then enter, and all you have to do is go change the sample size to 900 for B. Still too big. Remember, it's got to be less than 0.1 or equal to 0.1. So that's the answer for C. Still slightly too big. Make sure I have the answer right in my head. Okay. Still slightly too big. So I'm assuming, since we're getting closer and closer, this next one's going to work. But just to be safe, 1600. There we go. So that is the smallest one that makes this whole scenario work. All right, number 6. X is a random variable with a skewed distribution, gives us a mean, gives us a standard deviation based on a random sample of size 400, and then it's talking about the sampling distribution. So remember, sampling distribution is if you have 400 samples, you have 400 little X bars all on top of each other, making up this distribution. So it's asking about this distribution. What is the shape? I drew it as normal, but is it normal? What's the mean? What's the standard deviation? Okay, so here was the idea. The mean, if you look, is not really giving you a choice. The mean here is 10, no matter what, because it's matching up with the population. Standard deviation, this is where you can use that formula we just talked about on the previous problem. It's the standard deviation over the square root of the sample size. So that's 10 over 20, so that's really 0.5. So just based on that alone, the answer is either, oops, sorry, I should not have crossed out E. E is still an option. C or E, right, because they both have a mean of 10 and a standard deviation of 0.5. So the only choice here is it highly skewed like the original population, or is it approximately normal? This is where we had what we called the central limit theorem that told us if our sample size is at least 30, that the sampling distribution will even out and become approximately normal. So actually the answer is E. Okay, but this whole greater than 30 thing, that had a purpose. We've memorized it, but not the purpose. All right, number 10 was a formula problem. We've gone over that a few times now. So this is talking about confidence intervals. The minute you see that plus or minus, you should see that. It does say proportion, so keep in mind we're doing Z procedures. She wants to determine if the proportions for something is less than 0.5. So that would be like if we did a test, that would be like the null. She's given access to construct a 95% confidence interval. She selects a simple random sample of 100 births. So that is the sample size. I have a lot of guys that get this mixed up. That's like kind of the population in this case. And she found that 31% were males. So that together makes up our p-hat, 31 out of 100, so 0.31. So put that all together. You'll notice that 0.31 is the point estimate for all of those. That doesn't really help. So remember, formula for confidence interval is point estimate plus or minus, and then go back to what we talked about a second ago for margin of error. We have our critical value times our standard deviation of our statistic. I'm just writing the specifics for when it comes to proportions. So this part we've already figured out. Z critical value, remember, it's based on that interval percent confidence. So if you know it's 95% confident, then the wings has 5%, cut that in half, 2.5%. So your area. So let's put that in. It is Z, so we're doing normal, not invert T, we're doing invert norm. We're doing 2.5%. Again, it's gonna give me a negative, but I don't really care about that. Just 1.96 is fine. So what, plus or minus 1.96. So just based on that, I can get rid of D and B. Okay, and then put it all together. We had 0.31 for our p-hat, so that would leave 0.69, and then our sample size was 100, so that means the answer is E. Remember, when you're doing confidence intervals, you always use the sample data. So this 0.5 is just really there to confuse you. That would be if we were doing a test. That's kind of like the null hypothesis, and then that would become more of an important thing. We also had pooled proportions, but that was just for confidence or just for significance tests. So confidence intervals were the most basic. Don't overthink those. Okay, and then last but not least, we have number 18. And this is purely just, do you know your conclusion of a test? So even if you read down here, it says we did a t-test. We ended up getting the p-value already, assuming the conditions were met, which of the following is an appropriate conclusion. So get rid of any choices that don't even have a correct statement up front. So 0.08, 8.5% is less than 10. So these are all true. These are greater than 5%. So none of that we could cancel out, but sometimes you can cancel it out because that's not even a true statement. If it's less than the significance level, you are able to say it is significant, so you would reject the null. So on A and B, remember the P is low, reject the ho. On both of these, you would be able to reject the null, which if we look up here, we're investigating to see if the average number of text messages sent was greater than 100. So rejecting the null, we would say there is evidence of it being greater than 100. So if you read through those, it can be concluded that the mean number of text messages sent is less than 100. That's the opposite of what I just said. It can be concluded, it cannot be concluded. So again, read carefully. Neither of those are correct. Okay, so then we look through the other options. On all three of those, it's saying it's greater than the significance level, which is true. So that would be a fail to reject the null hypothesis. Fail to reject. So here we're saying that we do not have evidence of the mean being less. Oh, sorry, I keep saying less. I don't want to confuse y'all. The mean being greater than 100. Okay, remember this is what we were trying to prove. We were trying to prove that it was greater than 100. So if we're failing to reject, we should be looking for the answer that says there is not evidence of it being greater than 100. It can be concluded. Get that out of there. It can be concluded. Get that out of there. It cannot be concluded that the mean number of text messages sent is greater than, so the answer is B. I know some of us are still having issues with the wording of those, so if it helps on a If it helps on a problem like this, I might recommend actually writing out the null. The null in this case is that it's 100 text messages, and what we're really trying to prove is that it's the average is over 100. And so all of these ones where I said reject, we reject this and say this is being supported. If we fail to reject, then we just say this has not been rejected, this is still not being supported. Okay, I don't know if that helps at all, but kind of like just physically reminding yourself what you mean when you say reject, fail to reject. All right, that's it. Grab your practice sheet, which I believe is in blue.